Okay, so now we want to derive the mirror equations, all right? And this picture, I've copied it twice. It's basically right from your textbook. And we want to see how we can use similar triangles, which is pretty basic geometry, in order to derive the equations that govern where images will appear and how magnified they will be. So if we look at this picture, I want to highlight similar triangles that we're going to work with. Okay, so first of all, let me pick a really very different color that's quite bold here. Let me go with magenta here. Okay, the beginning of the proof is looking at this triangle right here. Okay, and that triangle is similar to this triangle down here. Okay, so we could say that O prime A O triangle is similar to, we'll say then that is triangle, what is that, I prime A I. Okay, so those two triangles are similar to one another. And so we know the proportions will be the same, all right? So if we look at that, well, then we could say that the vertical side of the first triangle mentioned, the top triangle, over the vertical side of the bottom triangle, which would be the object height and the image height, respectively, would have to be equal to the horizontal sides, right? Well, the horizontal side, OA, is what we call the object distance. OA is the object distance. And the other horizontal side, IA, is the image distance. So we have this relationship that we can start with, looking at that proportionality, right? So that's all we can get from the first pair of similar triangles. Now I've copied the diagram over to avoid getting too messy. And let me go back to this color. Maybe I'm going to do this with green this time, all right? So now we have a little triangle that we can look at right here. Okay, so that is triangle O prime FO. And then we're going to compare that to this triangle over here. Now, what I'm going to do, I'm going to drop a straight line down because this mirror really isn't supposed to be curved all that much. So there's a triangle, another triangle in here, and we can see that we have opposite angles over there, and opposite angles need to be equal to each other, and these are right triangles, so we have two angles that must be equal to each other, therefore all three angles must be equal to each other, and therefore those, the triangle O prime FO is similar to the triangle, let's see, what is that, FAB. Okay, now of note, this vertical side AB is the same distance as HI, all right? So we could say this height in here is the same as HI over there because we have a, I didn't draw it very parallel, but that red line, this red line right here, should in fact be a parallel line to the optical axis. So the height of that line stays constant. Okay, so once again, we have two similar triangles, and we can say HO over HI, the vertical sides, this time need to equal OF over FA, okay, the horizontal sides. Okay, but what is OF? OF is the distance from here to here, all right? I'm sorry, OF is just to, I didn't draw that very well. Let me just start that over again. If I were to draw a complete line from O prime all the way over to the plane of the mirror, we could divide it right here. And this size, that's OF. But the whole line is the object length. So this little part in here that's left is OF minus DO. I'm sorry, so OF, this part in here, is actually the focal length, pardon me. So how big is OF? OF is equal to the entire object length minus the focal length. So we could rewrite this as DO minus the focal length, which is, we use lowercase f for that. So we use capital F for the focal point, but lowercase f for the focal length, all right? And then we have this FA. Well, FA is just the distance from here over, which is, in fact, the focal length, all right? So now we can go ahead and we have two things that are equal to each other. Looking at the similar triangles, we can now say that the right-hand sides of both of those equations must be the same. So let me switch colors here. We can say that DO over DI must equal DO minus F over F, all right? So that's true, and we could solve problems with that, but that's not very useful. What we would much rather do is divide this up into a couple of terms, okay? And we can see that DO over DI is equal to DO over F minus F over F. All right, let me pause and gather my thoughts for just a second. Okay, there are several ways to take this to the finish line, but what I'm going to do now is divide every single term by DO. So I'm going to multiply everything by 1. I'll write it over on the side here. We're going to multiply by 1 over DO. Okay, so if I look at the first term and I multiply by 1 over DO, I end up simply with 1 over DI. If I look at the second term, the first on the on the right-hand side, and multiply by 1 over DO, I have 1 over F. And the last term, you could see that the F over the F is just 1. So if I multiply that by 1 over DO, then I will in fact have, that's a minus sign there, not an equal sign, minus 1 over DO. Now we can make this very symmetric by writing that 1 over the focal length. Actually, it's usually written the other way. We usually write the object length first, the reciprocal of the object length plus the reciprocal of the image length should equal the reciprocal of the focal length. Okay, so this is the mirror equation. We'll talk about using this in problems. It's very easy to use. We'll do that in the next video, all right? Now the magnification is another thing that we can figure out. So if we want to look at the magnification, it is simply M. This is, by the way, is the lateral. In other words, we're looking at the length of the image. So we'll put H of I over H of O. Okay. So it turns out if we go back up to some of the earlier slides, we will be able to show that that is equal to negative DI over DO. Okay, so the magnification will be negative DI over DO. Now it's slightly confusing if you go back and you look at the first equation that we have. We haven't looked at the magnification yet. Okay, the key is in this diagram, the image is inverted relative to the object. Okay, so but using the similar triangles that we have here, the ratio of the heights is given by this, but we were really looking at the absolute value of the heights. Remember, H of I is in the opposite direction, right? So if we want to look at the magnification, we add this negative sign to indicate that it's usually, if DI and DO are both positive and DO greater than 0, then M is less than 0, it's negative, which means that it is inverted. Okay? So the negative sign tells us that there's an inversion here, but we can find the magnification if we know where the image is and where the object is. We can take the ratio of the image length to the object length and take the negative of that. Okay, so we're going to apply that to a few problems in the next video.